In this video presentation, we will discuss sets and how it is used in mathematical language. By definition, a set is a collection of objects into a set or group. These objects are called the elements. Let's look at this example. Consider the set S that contains the numbers 1, 2, 3, 4, and 5. We can use the following notation as S represents the set and the numbers 1, 2, 3, 4, 5 are the elements of the set. This kind of notation is called the roster method. Sets can be written using a grouping symbol and by enumerating its elements. Also, one of the important notions in set is the concept of membership, or the belonging of an element to a set. We denote such membership like this. So it means that 1 is an element of set S. On the other hand, non-membership will be denoted like this, which means 6 is not an element of set S. Sets can contain finite or infinite number of elements. In the previous example, we had a finite set which is from 1 to 5. That is, it has limited number of elements. In this example, we consider an infinite set, that is, a set that has no limit in terms of numbers of elements. It is denoted by a continuous dot going to the right. This means that it also contains the numbers 6, 7, 8, and so on, or all positive integers. This is another example of an infinite set extending to the other direction. Notice that the continuous dot is going to the left. It means it also contains -4, -5, -6, and so on, or all negative integers. Also, we have an infinite set that extends to both directions. So notice that there are continuous dots on both left and right side of this set. This means that this set contains all integers. Here are some examples of commonly used set notations in mathematics. Now, what if I want to know the set containing all real numbers between 0 and 1, including 0 and 1? This example is a bit tricky. But this can be written as a set notation like this. This is called the set builder notation, and it can be read as S contains all x's such that x is greater than or equal to 0 and x is less than or equal to 1. You can also rewrite it further using other mathematical symbols like this. Next, a subset is a portion or a small group of set that is within a defined set, sometimes called as a proper subset. It can be written using this notation. It means 1, 2, and 3 is a subset of the set 1, 2, 3, 4, and 5. Now, consider the set 1, 2, 3, 4, and 5. We can also say that the set 1, 2, 3, 4, and 5 is also a subset. The set 1, 2 is also a proper subset of the set 1, 2, 3, 4, and 5. Now, 6 and 7 is not a subset since these two elements are not included in the original set. Also, 1, 3, 6 is not a subset since 6 is not included. Take note that the empty set or the null set is also a subset of set 1, 2, 3, 4, and 5. Next, the complement of a set is a set that contains the elements in the universal set which are not contained in a given set. For example, the set A, wherein the complement of set A denoted by A prime are the elements that are not included or not contained in set A. For example, consider the universal set U that contains these elements. If A or set A contains 1, 4, 5, and 6, then the complement of A or A prime are all the elements that are not included in set A but included in the universal set, which is 2, 3, 7, 8, 9, and 0. If set B are the elements of set 1, 2, and 3, then the complement of B are all the elements in the universal set that are not in the set B. Lastly, if C or the set C contains all the elements from the universal set, then the complement of C is a null set. Let us proceed now to set operation. The first operation for sets is the union or the union of sets. Consider sets A and B, where the union of sets A and B denoted by the symbol U is the set that contains all the elements that belongs to A or to B or to both. You can write the union of sets using this notation, or by a Venn diagram, the union of sets A and B looks like this. For example, let set A be the set with elements 1, 3, 4, and 5, and set B with elements 3, 4, 7, and 8. The union of A and B, or A or B, is equivalent to all the elements for both A and B, which is 1, 3, 4, 5, 7, and 8. The next set operation is what we call the intersection. So considering sets A and B, the intersection of the sets denoted by the inverted symbol for the union is the set of elements common to both A and B. It can be written with this notation, and using the Venn diagram is the intersection between the two circles. For example, let the set A be the set with elements 1, 3, 4, 5, and set B with elements 3, 4, 7, and 8. The intersection of A and B is given by the elements that are both the same for A and B, which is 3 and 4. Let's look at this final example. Let the universal set U be equal to the set of elements from 1 to 12 and set A, B, and C as follows. What is A intersection of the complement of B union C? Now, to solve this kind of set operation, you can solve it by parts. Begin with the union of B and C, wherein the union is equivalent to the elements 1, 2, 3, 4, 5, 6, 7, and 8. Now, since you need its complement, you can easily get the complement of the set as 9, 10, 11, and 12. Now, solving its intersection with A, the only elements that are similar to its complement and A are the elements 9 and 10. So the answer is the elements 9, 10.